Another thing we're interested in is system properties. If we have a system, we're interested in what's going on in that system. So things like the pressure, the temperature, all of these things, how much mass is in the system. You may not know this. This is a cross-section of a propane tank, or a cutaway of a propane tank. But propane in a tank exists in two phases. There's the gas and the liquid. When you pick up a propane tank and you shake it around, if it has a decent amount in it, you'll feel and hear liquids sloshing around. And so to tell how much propane's in the tank, there's actually a float in each propane tank, and that's what allows you to read out the level in the tank. Now, it wouldn't necessarily, typically there is a pressure gauge, but if you want to measure the level, you need a separate gauge for doing that. Anyway, properties in a system, if we take the system to be the inside of this propane tank, we're interested in, well, how much mass is in the tank, right? If we make a schematic of that system, here's some of the variables we were interested in: pressure, temperature, volume, mass, density. We'll use the Greek letter rho that looks a lot like a lowercase p. We'll use that to indicate density, and then U is internal energy. Now, if you think about those properties of the system, if you imagine putting a boundary right in the middle of the system, so you cut the system in half in your mind. Now think about what happens to the pressure. If you measure the pressure on one side and the pressure on the other, well, you'd find that they're the same as they were before. They're equal to each other now in our propane tank. Same thing with temperature, but half the volume's on one side and half's on the other. Half the mass, if it's uniformly distributed, is on one side and half's on the other. But the density would be the same on both sides, and if we're careful how we specify energy, we could either think of it as half of the energy on one side and half on the other, or the same on both sides. Now, how can we think of it as the same? I'll show you. We're going to define something called specific properties. I don't mean particular properties. What I mean is properties that are per unit mass. Now, did you notice something interesting? Did you notice that density didn't change when we imagined cutting the system in half? Well, what is density? Well, density is how much mass you have per unit volume, right? Well, that makes sense because it's mass per volume, and the mass that takes up a certain amount of volume doesn't change if you just imagine a smaller amount of volume. Now let's take this a slightly different way. I've got tank A here on the left in red, and if I look at the, let's say, mass, let's say we got 10 kilograms of something in the tank, and the volume of the tank is 2 cubic meters, pressure is 100 kilopascals, and the temperature is 15 degrees Celsius. Fine, whatever, just making that up, okay? Now, here's something interesting. Instead of dividing the mass by the volume, what if we divide the volume by the mass? So what if we take all the volume in the tank, the 2 cubic meters, and divide it by the 10 kilograms of mass that's in the tank? If we do that, then we'd find that we had 0.2 cubic meters per kilogram, just the inverse of density. Now, tank B, let's imagine taking tank A and cutting it in half. Not literally, but just dividing it, separating it into two parts in our mind. We've got that yellow dividing line. Well, now half the volume's on one side, half is on the other, half the mass is on one side, half is on the other. But the pressure and temperature still seem to be the same, which is kind of nice, right? It doesn't matter how big the system is or to what extent the system is taken, how big it is. The pressure and temperature are the same, and that's kind of nice. Well, what happens to this little volume thing we were playing with earlier? Well, let's consider one side of our blue tank now. The volume is 1 cubic meter, but we've only got 5 kilograms of mass, and so 1 divided by 5 is 0.2, just as it was before. That's kind of nice. You see, what's nice about this new property we've just discovered or we've just defined, which really is just the inverse of density, we call it specific volume, and we give it the symbol lowercase v, whereas the total volume has the symbol uppercase V. You might notice that. That was done intentionally. So the nice thing about specific volume is it doesn't depend on how much of the system we consider, or another way of saying that is it doesn't depend on the extent of the system. Now, you probably have done something like this. If you've ever gone shopping for groceries and you're trying to decide, should I buy cracker package A or cracker package B, and let's just say that both crackers are made by the same manufacturer, they're whatever you like, I don't know, club crackers, saltines, whatever, and you're trying to decide which one to purchase. One has more in it, one has less. Of course, the one with more has a higher price than the one with the fewer amount of crackers. You might look at that and say, well, which one do I want to purchase? And you consider the cost per ounce, right, or the cost per mass. You already do this, don't you? So a specific property is just something that is a per unit mass property, and it's something that's very useful in our study of systems and what makes them perform. So specific properties are just properties that are per unit mass. So if you have a cubic meter block and you put it on a scale so that you can measure its mass, and you find that its mass is 3 kilograms, well then take the volume, divide it by the mass, again it's just the inverse of density, and you'll find that you've got 0.33 cubic meters per kilogram in this particular instance. So this would not be a stone or something, right? It has too high a specific volume or too low a density. This is probably a block of foam of some kind. Okay. Now, there is a term that I don't like. It's called specific gravity, and I call it the joker in the pack of specific properties. The reason is because specific gravity is not a per unit mass property. So I actually prefer the term relative density, because specific gravity really is just how dense is this thing I'm looking at versus the density of water. And really all it tells you is whether something would sink or float in water at particular conditions. So, for example, if I have a rock specific gravity, I can tell you is, well, maybe not lava rock, but if you go out to your yard and pick up a piece of granite or even a piece of slate, its specific gravity is going to be higher than 1. It's going to have a density greater than the density of water. And so the way that we usually use specific gravity is you go and you look it up, and then you multiply it by the density of water to find out the density of the stuff you're working with, that you're referencing. Okay, so you can see that in the rearranged equation there, where rho sub s is the specific gravity of the substance. Unfortunately, rho is not really a good symbol there. Sg, I think, is a better symbol. But this is the way your author describes it, so I've left it this way. But Sg is a dimensionless thing, right? Specific gravity. It's density over density, and so the units cancel. Now, it turns out that water's density actually depends on its pressure and temperature, more so on its temperature than its pressure, and so we usually neglect the pressure dependence. Well, we're talking about the temperature of 4 degrees Celsius. So where water has a density of 1,000 kilograms per cubic meter, or 1.94 slugs per cubic foot, that's the density we're talking about. And that's the reference density of water. And unfortunately, I've used a different symbol here. I'm not trying to confuse you. I'm trying to give you a preview of what we'll do. I'll probably go back and forth between rho sub W and rho sub H2O. Those are the same things. I mean the density of water in both cases.